In this video, we will look at some problems that we solve when dealing with chemical equilibrium. But first, let's look at how this chemical equilibrium happens. Really, equilibrium is looking at a state where you don't see observable changes. So we can say that if you reach equilibrium for a system, you see no observable changes to the system. So when we talk about chemical equilibrium, really you are looking at a chemical reaction and you don't see any observable change. But how does this happen? First, we talk about reversible reaction or reversible reactions. So these are reactions that will go forward and backward. So that go both forward and backward. So these are reversible reactions. Now you will see that these reactions will reach a time when you can no longer see any change in that reaction, and at that point the reversible reaction will reach equilibrium. So at first, the reversible reaction, maybe we can have a lot of reactants forming more products, but there will be a time when we have formed enough products that the forward reaction will be equal to the backward reaction. At that time, we say we have reached an equilibrium situation for a chemical reaction. So an example is this reaction that we have here: dinitrogen pentoxide to form nitrogen dioxide and oxygen. So if you want to talk about this reaction as reversible, we can say that we have the forward reaction. Now we use a single arrow. So this is our forward reaction. We'll call it reaction 1. But we also have the reverse reaction. So this one is forward. We also have the reverse reaction. So that reverse reaction is 4NO2 gas plus O2 gas to give also gas. So we'll call that equation 2. Now, when you combine the two reactions, that's when you have your complete reversible reaction at equilibrium, especially when you don't see any change in its speed. So normally when you have an equilibrium reaction, you'll be given a double arrow. So that will indicate that this reaction is reversible, and the double arrow of equal length will tell you that this reaction is at equilibrium. Now, how do we write equilibrium expressions? So here we are using an example. Small a big A plus small b big B is in equilibrium with C, small c, big C, D, big D. So these A, B, C, and small d, they are coefficients of reactants and products, while the big A, big B, big C, and big D, these are the actual reactants and products. So when you have an equilibrium reaction like that, a reaction that is reversible at equilibrium, we can write down an expression that will give us an equilibrium constant, that is K. So you can have an equilibrium constant based on concentration. So this is K based on concentration. You can also have an equilibrium constant based on pressure. This is K based on pressures. So the concentration one is known as Kc. The pressure one is known as Kp. So C is concentration, P is pressure. If you have an equation like this one, and you want to write an equilibrium expression, let me start with Kc. Kc will be given by the concentration, the product of concentrations raised to the power of their coefficients, divided by the product, or let me say again, it will be given by the product of products to the power their coefficient, divided by the product, that is after multiplying, the product of reactants to the power their coefficient. So what we are saying is in terms of their concentration, that is. So we have the concentration of product, that is C, this C to the power small c, times the concentration of the other product, that is big D to the power small d. So the product must be on top. The products must be on top. Divide by the concentration of the reactant to the power the coefficient of that reactant, that is small a, times the concentration of the other reactant to the power the coefficient. So products always on top, reactants are in the bottom. So this is the Kc. Now if you talk about Kp, that is equilibrium constant for this concentration or for this reaction. In that case, we use pressures instead of concentrations. So we say the pressure of the products. So in this case, the product is C. The pressure of C to the power small c times the pressure of D to the power small d, divided by the pressure of A. So A is subscript and the small a is superscript. So put the small a here, and then the pressure of B to the power small so to the power small b. So that is the Kp. We can determine the equilibrium expression using both Kc and Kp. Kc is for concentrations, Kp is for pressures. Now let's look at an actual chemical equation, and we come up with both Kp and Kc. So we'll start with K, C, and Kp. So this K is big K, big capital letter K. So these ones are our reactants, or this is our reactant. These ones are our products. So remember, a Kc must be given by the products of products divided by the products of reactants. Here we have only a single reactant. Here we have two products. So we need to take note of the coefficients. So this, that, and a 1 here are the coefficients. So whatever reactants we have will be to the power these numbers. And then this and this and this one are the actual species, that is reactants and products. So the Kc will be given by the concentration of this product to the power the coefficient, that is 4, times the concentration of oxygen. So this oxygen will be to the power 1 because its coefficient is 1, divided by the concentration of dinitrogen pentoxide to the power this coefficient, that is 2. So that is the equilibrium expression using Kc. Now using Kp, it will be the pressure of NO2 to the power 4 times the pressure of oxygen divided by the pressure of N2O5. So this is an equilibrium expression using Kp. So we should be able to look at a problem and write down an equilibrium expression. One important thing about equilibrium expressions is do not include a solid when you want to write an equilibrium expression. Also, do not include liquids. An example is the equation given here. We have water, liquid, in equilibrium with the hydronium ion and hydroxide ion. Now if you want to write an equilibrium expression for that, it would be K, let's say Kc is the products, which is H3O plus, OH minus, and down here you put your water. But we are saying because this one is a liquid, we can't include it here. So we get rid of this. All liquids and solids, they are taken as one in the expression. So this one is an incorrect way of writing the equilibrium expression for this problem. The correct way is K, actually we call it Kw, as you will see later, is given by H3O plus and OH. So we just use the aqueous. We include gases, just these two. In equilibrium expression, include only the aqueous, not the liquid phase, and include the gases. These are the only two things that you need to include in your equilibrium expressions. So let's solve something based on what we have shown. So we have this equation, sulfur dioxide plus oxygen, to give us sulfur trioxide. And we are given equilibrium concentrations at a specific temperature, that is certain temperature. Sulfur dioxide is 0.2 0.90 molar. Oxygen is 0.35 molar. And sulfur trioxide is 1.1 molar. So what is the Kc for this reaction, the equilibrium constant for this reaction? So what you want to do is to start with the expression. Kc is given by the concentration of our product. So the coefficient here is 2. So this one should be to the power 2. Divided by the concentration of the reactants. So in this case, 2 to the power 2. And the other reactant, which is oxygen, to the power 1. From there, we just substitute the concentrations. So instead of sulfur trioxide, we have 1.1, but this is squared. Down here, instead of sulfur dioxide, we have 0.9, also squared. And for oxygen, we have 0.35. So in the end, our Kc will be let me just 4 point, that is to two significant figures, 4.3. So that is the Kc for this reaction. So that is the Kc for the reaction. Now let's look at another example. The same reaction, calculate Kp. So I'll just check the equation itself. So the equation is 2SO2 gas plus O2 gas in equilibrium with 2SO3 gas. Now we are given the pressures in atmosphere, which means we are determining the Kp. So the Kp for this reaction is P SO3 squared up there, divided by P SO2 squared, and PO2. P SO3 is here, which is 26.9 squared. P SO2 is here, which is 22.0 squared, and PO2 is given here, 8.56. So calculating this, we get 0.175. So that is our Kp for this chemical reaction. So let me just do the calculation again to see if it is correct. Squared divided by 22 squared times 8.56. Yeah, so it's a correct answer. So that is the Kp for this reaction. You can see that I'm not really concerned with the units of the Kp. Sometimes the reaction is actually not at equilibrium. So in that case, we do not use Kp. We use what we call reaction quotient. So reaction quotient is like Kp or Kc, but the reaction is not yet at equilibrium. So it is as the reaction is approaching equilibrium, it has Qc or Qp. When the reaction reaches equilibrium, then it has Kp or Kc. In other words, we can say Kp is a Qp but at equilibrium, or Kc is a Qc but only at equilibrium. At any other point other than equilibrium, we have Qp or Qc. So if you have a reaction like this one, the same reaction that we had last time, the expression will be the same, but this means reaction not yet at equilibrium. That's what it means. So why is Qc important? Because anytime QC is less than K, or maybe instead of QC I'll just say anytime Q is less than K, the reaction will proceed to the right. So the reaction will move towards the product. So you can do your calculation and say, what is the Q of this? You find your Q and you compare it to the K, and you see that Q is less than K. That reaction is moving towards the product. It means the reaction is going this way until it reaches equilibrium. Now, if QC is greater than K, or if Q is greater than K, then the reaction will go backward. It means you have more of this than this, which means you need to form more of this to compensate for that. Now, if QC is equal to K, then the reaction is at equilibrium. So let's see how we can use that information. Now, in your handout, we'll have this as example 3. Make sure that you check this example in your handout and check this video. Using the given concentrations, determine if the following reaction is at equilibrium at 20 degrees Celsius. So you will see that all the time there will be a temperature there. So we are given pressures, not actually concentration, but we are given the pressures to find if this reaction is at equilibrium. So what we are going to do, this is our Kp. So what we are going to do is to determine the Qp and compare it to this Kp. So for this expression, Qp is given by P squared ICl divided by P I2, that is the pressure of I2 and the pressure of Cl2. Now substituting this with numbers, PICl is 0.355, but this one should be squared. PI2 is 0.114 and PCl2 is 0.102. Now doing the calculation, so the Qp in this case is 10.8. Take note, here we are using 3 significant figures. So the Qp is 10.08. Now what do we see here? We see that Qp, which is equal to 10.8, is less than the Kp, which is 81.9. So the question is, Is this reaction at equilibrium? The answer is no. The reaction is not at equilibrium. The reason is QP is not equal to Kp. Now, what will be the direction of this reaction? We see that Qp is less than Kp. This means that the reaction will go forward. So that's how we use QP to understand what is happening before equilibrium, or what the direction of the reaction will be. So you can have another question where the QP will be greater than Kp. In that case, the reaction will go backward. So here, when we say forward, we mean to the right. Right direction. So make sure that you watch this video and you go about how to write an equilibrium expression, how to determine an equilibrium constant when you are given a reaction, and also how to determine the direction of a reaction using the reaction quotient and comparing it to the equilibrium constant. Thank you.